In this module, we're talking about average atomic mass. Well, we know that an atom consists of the nucleus and the electrons, and that within the nucleus there are protons and neutrons. The only thing that determines which element any given atom is how many protons there are. For example, any atom in the universe that has 81 protons is the element thallium. But because different atoms can have the same number of protons but different numbers of neutrons, they have different masses. And it ends up that every element that occurs naturally on Earth has the same percent abundances, the same fractions of the isotopes that make it up. And that makes it pretty nice for us. So first of all, how do we know this? How can we prove this? How do we detect it? Well, we have this really cool instrument called a mass spectrometer. And this is the schematic of basically how it works. Real briefly, so whatever you want to analyze, now we use mass spectrometers for large molecules, but right now we're only talking about single elements, neon or something. So we have the sample of whatever we're going to analyze, and we have to vaporize it. If it's not already a gas, we have to heat it up and make it a vapor. We can make anything a vapor. Then we have different ways of ionizing the atoms that go through here. In this schematic, it shows an electron gun. There are other ways to do it. It doesn't matter. Basically, think about this as an electron gun that knocks electrons off of these atoms as they're passing through here. Well, why do they even go there? Well, we have this stream of particles going in here, and we have, once we knock one or more electrons off, then we have positively charged particles. And we have electrically charged plates here. This would be positively charged, and this would be negatively charged. And so that means that as this beam goes through here, once it passes through here, it's repelled by this plate and attracted by this plate, and it accelerates these particles. Now they're moving really fast. And now as they're going down here, we also put a magnetic field outside of that stream. Now it ends up that any charged particle that's moving also has a magnetic field associated with it. And that means that it acts like a magnet, which means that it gets attracted or repelled by different poles of a magnet. And so it ends up, as these particles are zooming through here, and they go through this magnetic field, this magnetic field causes these particles to curve. So, think about some neon gas going through here, knocking some electrons off, and then we have neon cations, okay, going through here, and they're curving. Now, just like if you have a motorcycle and a big truck going at the same speed, the motorcycle can turn a lot more sharply than that big truck can. The lighter particles make a sharper turn than the heavier particles. And so we get this spread of the particles based on how much they weigh, basically. And so we have a detector over here that basically it counts how many particles hit at each place. And then the computer analyzes it, and it tells you, at this mass, how many particles were there. And we get something that looks like this, roughly. Okay, this is a simplified version. But we have the relative number of atoms on the y-axis and the mass number. That is how much, basically how much each nucleus weighs. The protons plus the neutrons is the mass number. And it ends up that for neon we get something that looks like this. At mass number 20, relatively speaking, these are percents basically. We get 91 out of 100 hits are neon 20. Only 0.3, less than 1 out of 100, are neon 21. And 8.7 out of 100 or so, about 9 out of 100 are neon 22. So remember, these are all neon. So all of these atoms have 10 protons. This one has 10 neutrons, this has 11 neutrons, and this has 12 neutrons. So when we do this, we can get a ratio of masses of these different isotopes. And the standard that has been chosen is that of carbon-12. That is an atom of carbon that has 6 protons, which makes it carbon, and 6 neutrons. And if we take the ratio of the mass of any element, any isotope, to the mass of the carbon-12 isotope, we get a ratio, get a number. For instance, taking carbon-13, the ratio of that to the mass of carbon-12, we get 1.0836129, some number. You don't have to remember that number. But what we do is, because we define, our system is based on carbon-12, we define the mass of an atom of carbon-12 as being exactly an infinite number of sig figs, exactly 12 AMUs. This also, by the way, gives us a definition of an AMU. AMU stands for atomic mass units, and it's just a unit of mass that we use when we're using these really small things. So the definition of an AMU is exactly 1/12 the mass of a carbon-12 atom. So anyway, now that we have defined the mass of carbon-12 as being exactly 12 of these AMUs, we can rearrange this a little bit and get the mass of any other isotope, in this case carbon-13. So just rearrange this and we get 13.003354455 AMUs for carbon-13. Now that we have defined carbon-12 as the standard, we can do this for any isotope. So because every element that occurs naturally on Earth has the same fractional abundance, the same fraction of each of the isotopes that makes it up, we can do this little calculation here. This formula, which you should remember, says that the average atomic mass of an element is equal to the fractional abundance of the first isotope times the mass of it, plus the fractional abundance of the second times its mass, and so on, for however many isotopes there are. If there are only 2 isotopes, then there's no third term. If there are more, then there are more terms. Now, the average atomic mass, what we're calculating here, if we were to scoop up a handful of, say, carbon, okay, and figure out, on average, how much those atoms weigh, it ends up that it's about 12.011 AMUs on average. And that comes from basically this calculation right here. It's a weighted average, like we did with the bronze cylinder or the pennies, right? The same thing, that's the weighted average. Now, the thing is, okay, so carbon, right, it ends up that the average mass of carbon is about 12.011 AMUs. That's the average atomic mass. Now, there is no atom of carbon that has that mass. There's carbon-12, carbon-13, and a couple other isotopes, but none of them has a mass of this. This is a weighted average. So, I'm going to get back. So now we can use that formula to do some calculations. So we're going to do this example. Take a moment and read it. Okay, so first of all, what we want to find are the percent abundances of the 2 thallium isotopes. And what we're given is the average atomic mass of thallium and the isotopic mass of the 2 isotopes. We're told there are only 2 naturally occurring isotopes. Well, if we can find our F's, our fractional abundances, the percent abundance is just 100 times that fraction. But we don't know either one, so basically we have 2 unknowns. We need another equation, but that's it right here. Because there are only 2 isotopes, their fractional abundances must add up to 1, just like their percents must add up to 100%. And so if we rearrange this, we can solve for the fractional abundance of isotope 2. 1 minus, whoops, that's a typo. It should be 1 minus F1, shouldn't it? Now let's fix that. Anyway, plugging the numbers in, okay, this is the average atomic mass of thallium, which we were given. By the way, you'll always have a periodic table. You look this up. This is the number. The average atomic mass is the number on the periodic table. So you look this up. If you look at the periodic table, you'll see that's thallium's average atomic mass times the fractional abundance of the first isotope times its mass, and 1 minus F1 times the second. Now, it doesn't matter really which you call 1 or 2, F1 or F2, but what I do to avoid any confusion is I always make the sub 1's the lightest isotope, the sub 2's the next heaviest, and if there's a third, F3 and M3 would be the third heaviest, and so on. That just avoids any confusion. Doing the algebra, solving for F1, check my algebra, make sure you get the same number. Get 0.2952 sub 4. We get 4 sig figs because of this subtraction right here gives us 4 places past the decimal, and that's 4 sig figs. Because we know the fraction of the first isotope, which is thallium-203, the fraction of the second, thallium-205, is 1 minus that, so 0.7047 or 8. And the percents are just 100 times the fractions. So there's our answers right here.